On the bench today we have a classic HP instrument, a HP 8614B signal source. This generates 800 megacycles, none of this Hertz stuff, through to 2.4 gigacycles. I'm not even going to put power on it today. What we're going to look at is the mechanics of this. So one of the problems that the HP engineers had to solve was how to set the display here to show the frequency. It had to be between 800 megacycles and 2.4 gigacycles, or in the display it would have been 2400. So this display here has to turn a set number of turns from 800 all the way through to 2.4 and no further. Well, just a little bit further. It had to stop at almost exactly 2400, and when you go back it has to stop at almost exactly 800 megacycles, like that. So how did they do that? How would you do it? That's the question that we're going to answer today. So the HP solution on how to limit the number of turns that either the frequency or the attenuation could turn is simple and elegant. It is based on two gears engaging with each other, and those gears include one which has a set screw sticking out of it in between a couple of the teeth, and the other gear has a bent tooth. And what happens is that when these are turned just the right number of turns, the bent tooth hits the set screw. Now, I haven't counted the teeth on these, but if one gear has got 19 teeth and the other gear has got 20 teeth, then each revolution that the shafts make, the gear will advance by one tooth on each revolution. So you could have up to 19 revolutions of one shaft relative to the other before the set screw and the bent tooth collide and stop the rotation. And that is how the Hewlett-Packard engineers limited the number of revolutions. A very elegant design. The engineering magic of Hewlett-Packard engineers didn't end there, because when you adjust the frequency, you have to adjust the position of a piston inside the Klystron. And there is a non-linear relationship between where the piston is and the frequency that you select on the input shaft here. So what the Hewlett-Packard engineers did was use these two cams. Now from this angle it looks like the cams are operated by friction. But what actually happens is that there is a cable that is threaded around through slots, and it goes from one to the other cam, right? And then there's another one that goes round this way and over here. So it's not friction that's driving these cams, it's actually a steel cable. And these cams mean that the nonlinear relationship between input shaft frequency selection and where the piston needs to be in the Klystron can be highly nonlinear, but all the hard mathematical calculations are incorporated into the shape of the cams. So the operator doesn't see this. All the operator sees is that when they wind the cranky handle and change frequency, they get the frequency they want based on a nonlinear relationship between the piston inside the Klystron, which is in a tune cavity, and the crank. The quality of the HP engineers' work didn't stop there, and what they did to make it easier to service was they put this printed circuit board on here, which would have been an early application of printed circuit boards. They put on this aluminium chassis, which is hinged and held down with a couple of screws, which I've removed. so that when you want to service this instrument, you undo the screws and just fold out the valves, and there you have the circuit. And along here, it's almost like they've got the manual etched into the chassis, so you can see where things are. The Klystron itself, which this is based on, all this electronics here is to support the Klystron. Klystrons are a variable frequency oscillator, and they are still used today because they can put out huge amounts of RF power. One of the problems that the Klystron solved was that a fundamental issue with valves is the physical distance that the electrons have to travel limits the frequency. If the distance is far, then it takes longer for the electrons to travel, and so the frequency that you can operate is less. The Klystron solved this by streaming out a constant beam of electrons and then modulating that beam with a standing wave. And what would happen is that electrons on the front of the standing wave would get pushed forward. Think of surfers on a wave, on the front edge of a wave, and electrons on the back of a standing wave would get pushed back. So the electrons would bunch up together at a frequency set by the tune cavity and not by the distance the electrons have to travel. So as they passed down the tune cavity, it would go from a constant beam of electrons to a modulated beam of electrons, modulated by the dimensions of the tune cavity. And with that, you could end up with an instrument that could produce 0.8 to 2.4 gigacycles output. Quite unremarkable by today's standards, but at the time this was bleeding edge technology. You can see the quality of the engineering design in this is typical of HP of the era, and that's why HP became an industry leader.